Okay, notes 5.7 is the second derivative test. So remember in 5.6, when we were trying to find concavity, we were using the second derivative test. We just didn't give it a name. Okay, so just like when we talked about the first derivative test. So when you see the second derivative test, this is used to find relative extrema. Extrema. Okay. It can also be used to determine concavity. So in part A, using the graph off to the right, it wants us to identify the relative extrema. And so for this, we're looking at either the peaks or the valleys. So when it's either concave down or concave up. Okay, so that means we have one right here and one right here. Okay. And then it says, what do we know about the value of the first derivative at each extrema? So notice this is the graph of f, which means that the first derivative at each of these points are going to be equal to what? 0. So we know that the first derivative is equal to 0 because we have a 0 slope. Okay. Then it says, what do we know about the value of f double prime of x at each extrema? Okay, so for example, what would we know about this one up here? It does change signs. So looking at just this point, is this concave up or concave down? Concave down. And when it's concave down, we know the second derivative is positive or negative? Negative. So here we know that the second derivative is less than 0. And that's because it's concave down. Which means the other relative extrema, since it's concave up, is going to be what? Greater than. So the second derivative will be positive or greater than 0. Okay, so that answer is C. So before we start talking about the second derivative test, I want to remind you what it means to do the first derivative test. So off to the side, we have the first derivative test. Okay. So for the first derivative test, that is helping us find if we have a relative max or a relative min. So for a relative maximum, we know that the derivative changes signs from positive to negative. Okay. For the relative minimum, we know that the derivative changes signs from negative to positive, the opposite. Bless you. Okay. So if the derivative, and we're still talking about the relative min here, if the derivative changes signs from negative to positive, what can we say about the function? Changing directions from decreasing to increasing, right? If our derivative is negative, we know our original function is decreasing. if our derivative is positive, our original function was increasing. So we can even relate this further to the function. We would say that f changes from decreasing to increasing. And the opposite would be true for relative max. Okay, so we would say f changes from increasing to decreasing since the derivative changes from positive to negative. Okay. Any questions so far? So off to the side was kind of just the recap from the past couple notes. Okay, now looking at our definition for the second derivative test. It says, suppose f prime of c is equal to 0, then if f double prime of c is greater than 0, then f has a relative minimum at x equals c. And then if f double prime of c is less than 0, then f has a relative maximum at x equals c. So that's the same thing that we identified on the graph above. Okay, so if our second derivative is positive, that means we have a concave down, or sorry, concave up. If our second derivative is positive, meaning greater than 0, that means we have concave up, which means we have a relative minimum. Right, we can't have a minimum if it is concave down. That'd be the opposite. Okay, and then if the second derivative is negative, then we have a relative maximum because it's concave down. Okay. So in the first example, it says use the second derivative test to find the relative extrema of f of x is equal to x to the fourth minus 2x squared. So that means we need to take the second derivative. So first, I'm going to take the first derivative. So what would the first derivative be? 4x cubed minus 4x. Okay, so before I find that second derivative, I'm going to go ahead and set my first derivative equal to 0 to find my potential critical points. Okay, so I'm going to set this equal to 0. And so when I'm doing this, I can take out a GCF of 4x, and I'm left with x squared minus 1. Okay. X squared minus 1 is a perfect square factor, so how could I factor that? X plus 1, x minus 1, which means I have 3 possible critical points, and that is at x equals, correct, x equals 0, x equals negative 1, and x equals positive 1, and that's when I set each of those factors equal to 0 separately. Okay, now I'm going to find the second derivative. What would the second derivative be? (12x squared minus 4). Okay. And then what I'm going to do, I'm going to take all of those potential critical points from the first derivative test, and I'm going to plug them into the second derivative. Okay, and then depending on what number they give me is going to tell me if I have a relative max or a relative min. Okay, so I'm first going to plug in 0. So f double prime of 0 means I have 12 times 0 squared minus 4, which gives me 0 minus 4, which is negative 4. Then I'm going to plug in negative 1. Let's go in the order, negative 1. So this would be 12 times negative 1 squared minus 4. So that negative 1 squared is positive 1. So 12 times 1 is 12. 12 minus 4 is 8. And then we'll plug in x equals 1. which since we're squaring that term, we're going to get the same answer of 8. Okay. So then based off the values we got, which one would be our relative max? At x equals 0, why? Good. Because this was, okay, we could say because it's concave down, and also the second derivative is negative. Okay. So this would be our relative max at x equals 0. Okay. Since f prime of 0 gave us 0, so that's that first derivative test, and f double prime of 0 is negative. It's less than 0. Okay, so notice when we're defining relative max and relative min, we had to have two pieces of justification. We had to use the first derivative test for justification and the second derivative test for justification. Okay, it would not be enough to just write one of them. Okay, so since that is our relative max, what would be our relative min? It would be good, both of them, right? Because they're both equal to the same number. So our relative min would be at x equals -1 and 1. Okay, so we would say our relative min is at x equals plus or minus 1. Okay, and we would use the same justification. So we would say since f prime of 1 and f prime of -1 equals 0, and that f double prime of 1 and f double prime of -1 is greater than 0. It's positive. Okay. Preferably, we would want to use the definitions of first and second derivative tests to justify, but if you want to talk about concavity, that would also get you the point for justification. Okay, any questions on 1? Okay. Number 2 says use the second derivative test to find the relative extrema of f of x is equal to the square root of 2x minus 2 cosine x on the interval 0 to 2 pi. Okay, so it's important that they gave us that interval, because what that means is if we find any extrema points that are not on that interval, then we cannot use them in our second derivative test. So first, we're going to do the first derivative. Okay, so remember, let's see. No, okay. So what would be my first derivative? Square root of 2. And the next term? Plus 2 sine x. Oops. Okay, plus because the derivative of cosine is negative sine, so that negative and negative became positive. Okay, so then from here, we are going to set this equal to 0 to find our potential critical points. And so I'm going to subtract the square root of 2 over. Okay, so I have 2 sine x is equal to negative square root of 2. And then divide by 2, so I have sine x is equal to negative square root of 2 over 2, which means I have two possible x values, one at 5 pi fourths and the other at 7 pi fourths. This would be a good example of why it's nice to have the unit circle memorized. Okay. And remember, I didn't choose anything outside of 2 pi. okay, because 2 pi was the end of my interval. I had to stay within that. If you had the option to use the calculator on this part, you could plug this into Desmos, right? But know that you're not going to get it looking nice and pretty with pi. They're going to give you decimal answers. Okay, so just keep that in mind as well. Okay, so now we're going to do the second derivative. Okay. And what would be the second derivative? 2 cosine x. Square root of 2 went away because it's a constant. The derivative of sine is cosine, so this became 2 cosine x. Which means from here, we're going to plug in our 2 potential critical points into our second derivative, and this is going to determine if we have a relative max or relative min. So I have f double prime of 5 pi fourths, okay, so that it's equal to 2 cosine of 5 pi fourths, okay, which is equal to 2 times negative square root of 2 over 2. Which gives us negative square root of 2. Again, if you had the option of calculator on this part, you could plug it in, but you wouldn't get that nice negative square root of 2. It wouldn't, I wouldn't say it would matter too much because we're just looking to see if that's negative or positive, right? So if you got a negative answer, then you would know you'd have a relative max. A positive answer, you'd have a relative min. Okay, then we're going to plug in the other one, 7 pi over 4. And this is equal to 2 cosine 7 pi over 4, which is equal to 2 times positive square root of 2 over 2, which gives you square root of 2. Okay. So by doing the second derivative test, we know that we have a relative max where? Relative max at x equals 5 pi over 4. Okay, and again, you would use that same justification. So we would say, since f prime of 5 pi over 4 equals 0, and f double prime of 5 pi over 4 is less than 0. It's negative. Okay, which means we have a relative minimum where? 7 pi over 4. So we have a relative minimum at x equals 7 pi over 4. Since the first derivative of 7 pi over 4 equals 0, and the second derivative of 7 pi over 4 is positive or greater than 0. The next part says if there is only one critical point, and that critical point is a extremum, extremum, okay, which means it's a max or a min, then it is an absolute maximum or minimum. Okay, so if we only have one critical point, that critical point has to be a maximum or a minimum, then we can infer that it's going to be an absolute maximum and minimum, not a relative. So we're going to see that in this next example. Okay, so we have f of x is equal to negative x times e to the x over 4. So we're going to take the first derivative. And then notice we have two functions here, so we're going to use what rule? The product rule. So I'm going to take the derivative of negative x, which is negative 1, and then write e to the x over 4 plus, then I write my first function, negative x, and then I take the derivative of e to the x over 4, which involves what rule? The chain rule. So I have ex over 4 times 1/4. And then we're setting that equal to 0. Okay, so I could simplify this first before I start trying to solve for x. And I get negative e to the x over 4 minus xe, well, minus 1/4. Let me move that 1/4 to the front. Minus 1/4 xe to the x over 4 equals 0. Okay. This means I can take out a GCF of negative e x to the 4th. And I get 1 plus 1/4 x equals 0. Okay. So then from here, I know that I can only set that second parenthesis equal to 0 because there's no way for me to get negative e x to the over 4 equal to 0, because if I plugged in 0 for x, e to the 0 gives me 1. Okay, so we're not able to get this one equal to 0. I mean, we can't use this one. So I'm only going to use the parentheses. So 1 plus 1/4 x equals 0 implies that x is equal to negative 4. So I subtracted 1 to the other side and then multiplied both sides by 4 to get rid of that fraction. So x is equal to negative 4. Okay. Then I'm going to take my second derivative. So notice here I only got one critical point, and that is that x equals negative 4. So then taking my second derivative, okay, so I'm going to take the second derivative from, I mean, it doesn't matter where. I could go from my most simplified one, or I can go from before I took out the GCF. And so I think that is what I'm going to do. So then I get the derivative of the first one, which is that negative 1/4 e to the x over 4 because of the chain rule. Okay. Plus 1/4 negative e to the x over 4 times 1 plus 1/4 x. Okay, so I took the derivative of that second part, which is that negative e to the x over 4 times 1 plus 1/4 x. I took off for the chain rule, I multiplied by 1/4. And then I multiplied using the product rule, and that's why I have that extra 1 plus 1/4 x. Okay. So then, simplifying this, okay, I can take out the negative e to the x over 4 again. Okay. Which means I have negative 1/4 minus negative 1 plus 1/4 minus 1 times 1/4. So this is 1/2 plus 1/16 x. Okay, so again, this was me taking these and distributing it in and then combining like terms. So that's where that 1/16 came from, because 1/4 times 1/4. Okay. So then to find that maximum or minimum, I'm going to take x equals negative 4 and plug it into my second derivative. So f double prime of negative 4 is equal to negative e to the negative 4 over 4 times 1/2 plus 1/16 times negative 4. Okay. This is going to give me negative e to the negative 1. And then I have 1/2. So that's minus. Minus 1/4. Okay, yep. Which gives me negative e to the negative 1 times 1/4. 1/2 minus 1/4 is 1/4. Which I know is what? Positive or negative? Negative. So this is less than 0. It's negative. Okay? Which means I have an absolute maximum. And again, we know it's absolute because I had how many critical points? 1. Absolute max at x equals negative 4. Since f prime of negative 4 gave us 0, and f double prime of negative 4 is less than 0, okay? And then since we are saying this is an absolute max, I have to give one more form of justification, and that is to mention that negative 4 was the only critical point. So, and negative 4 was the only critical point.